Hello. Okay, wait. Hello, everybody. Welcome back to my channel. Last video, we discussed what are PROTACs. You know, what are the mechanisms? What is ubiquitin? How does it transfer to the protein of interest? How do PROTACs result to proteins of interest being degraded? Today, we're going to be talking about a little bit why that's significant. What makes PROTACs a more innovative drug than inhibitors, or like this next step to inhibitors, right? So the first section of this video is going to be just the benefits of PROTACs. So that means we're going to talk about selectivity, why it's more selective than inhibitors, toxicology profile, and the resistance profile, meaning like what resistances can develop to cause resistances to PROTACs versus inhibitors resistance profile, meaning like resistances that need to be developed for inhibitors to not work on proteins. Now, before we get into a little bit of the mechanisms that allow PROTACs to have a different type of selectivity that is more specific than inhibitors, let's get into a little bit of background information that you need to know. Some of it was covered in the last video, some of it we're covering in this video. So, first of all, if you didn't watch the last video, a PROTAC's goal is to join this naturally occurring E3 ligase, which transfers a signaling protein called ubiquitin. It's a 76 amino acid long protein that just signals to this proteasome, hey, this protein needs to get destroyed and broken into other peptides, right? So an, a PROTAC connects this E3 ligase to a protein of interest, which is just a protein you want destroyed. It's a protein that does something you don't want it to be doing. So a lot of times this is an oncoprotein that causes cancer. So it has one site that binds to the E3 ligase. It has this linker molecule, and then it has this other site that binds to the protein of interest, right? And the main goal of a PROTAC is to make these two close enough so that this ubiquitin can get transferred to the protein of interest. So now the protein of interest has a ubiquitin and is signaling to the cell, hey, this protein needs to get degraded into peptides. Now, a little bit of vocab before we start. Um, this right here, so when the PROTAC binds to the E3 ligase, and it's also binding to the protein of interest, when that step is occurring right before the ubiquitin gets transferred, that whole thing is called a ternary complex. This is going to be important in the next section of the video, which is the mechanism as to why that creates selectivity. Okay? And then a little bit of a correction from last video. So last video, we analyzed a figure which was describing the mechanisms of how ubiquitin gets transferred, right? So I did a little bit of a mistake on my part. I described the SBD as being the E3 ligase. That's not the case. The E3 ligase refers to a complex containing the SBD, the substrate binding domain, the scaffolding protein, and the adapter proteins. So that's just a little correction from last time. All right, now for the mechanism section. So to start with the mechanisms, I'm going to start with a little bit of a less scientific analogy to kind of introduce the idea. Okay, let's say you have this problem, right? You have a very specific belief that 3 people going to Six Flags is the perfect amount, right? And you want to go to Six Flags, so you invite friend A, right? You want to invite 2 people, and let's say these 2 people have no connection to each other. Your goal is to find 2 people who you think would have a good time together. Who are fun, who are energetic, who can go out, who are outgoing, right? You're looking for those extroverts to have a good time. So that's like in an abstract way, that's kind of the selectivity mechanism behind PROTACs, right? It's taking 2 proteins that never really interact and saying, hey, how can we design a drug that allows for favorable interactions, right? So it's like being a facilitator among friends, like inviting friend of friends to people to places, getting them to hang out with really really good friends, things like that. Now let's get into the sciencey stuff. So the extra layer of selectivity comes from the formation of the ternary complex. So what does that mean? Why is that? Let's talk about it. So let's draw these. So traditionally, inhibitors generally just have selectivity for, can it bind to the binding pocket well, and how well can it block the binding of ATP or other things to the protein. But PROTACs work a little differently in the sense that their goal is to form or is to achieve something called complementary surfaces. What does that mean? Well, it means that the two surfaces of the protein, the surface of the E3 ligase and the surface of the protein of interest, have to have favorable interactions. Now, favorable interactions, it can mean many things, but I think of it as this individualistic thing because proteins are very, very different, and also ternary complexes are very, very different from one another. So it's just about how well the interactions help you get to the shape of the ternary complex you want, right? So that's the mechanism behind the selectivity. That's why PROTACs will always be more selective than inhibitors. And before I get into the next example, which I think is a pretty cool example of this, I want to just preface one thing, which is that in a PROTAC, which is anchor, linker, warhead, the warhead is usually a commonly used inhibitor for the protein, right? It's usually, so like, for example, we talked about this last video. So there was arginine, ARG-PEG1-DASA. DASA is Dastinin. It was used to treat chronic myeloid leukemia, right? Dastinin was by itself used to treat chronic myeloid leukemia, and then arginine, PEG1, DASA was then a PROTAC used to treat that exact same disease. So what you're going to see if you read a lot of literature is you're going to see a lot of inhibitors that were already used to treat that disease used to develop PROTACs because like you've already done the hard work of creating the drug that binds to the protein. You just now have to figure out how you can create those complementary surfaces. So now we're going to get on to the specific example that I like. Now let's talk a little bit about exactly how much more selective PROTACs are than inhibitor drugs. So one of the examples that I use is from a paper that I'm going to cite at the end of this, and you should read it yourself. It's a very very good paper, but it's about this inhibitor and this SGK problem. So very very brief background is that SGK is a downstream protein in acute myeloid leukemia. It's a lot of the times an alternate pathway that gets favored for and exhibits oncogenic properties when there's inhibition on this AKT path, but that's a little bit of that's a topic maybe for another video, but also it's a very long topic. So we're gonna just talk about this SGK example. So in this example, this not example, this is a real life situation. In this situation, you had an inhibitor, right? And they wanted this SGK3 protein to be inhibited. It was the protein that was exhibiting oncogenic properties. It wasn't necessarily an oncoprotein because it's not mutated, but it's a protein that is exhibiting oncogenic properties, right? But there was a problem, okay? The problem was that SGK1 and SGK2 had very very similar structure in the region where the inhibitor binded to. Now, the reason this is important is because this inhibitor couldn't necessarily distinguish between any of these three proteins. So you ended up with a lot of these off-target proteins being affected by the inhibitor, along with the fact that there's resistances that can be developed if the inhibitor can't bind. It's just a little bit messy when this inhibitor is just involved. But do you know what they did? What they did is they slapped this same exact inhibitor, they slapped it on a PROTAC. They said, hey, we're going to make this a warhead, linker, anchor, and then this PROTAC was only selected towards SGK3. Okay? Now, the reason for that is that, once again, this ties back to that last idea we're talking about, where there was additional layers of selectivity, because there is an inherent need for selectivity in order to form the ternary complex, in the fact that the surfaces of the two proteins that are involved in the ternary complex, the E3 ligase and the protein of interest, in this case it's SGK3, they have to have favorable interactions with one another in order to form a ternary complex. And the selectivity is so much more that it even bypasses inhibitor selectivity. Like, so inhibitors that were already not that were already selective are being having increased selectivity when added to PROTACs, which I just think is such a cool example of human innovation in the field. Now we're going to get on to a little bit of what I think is like the from a toxologic, okay, how do I say that? From a perspective from toxicology. Okay, so the next point I'm going to make is about toxicology and the resistance profiles. So let's get into it a little bit. So first of all, now, while the toxicology is not yet explicitly better than TKIs, it has a little bit more potential. Now let me talk about that a little bit. When a drug is dangerous, it usually means, especially drugs like inhibitors, it's because of a lack of selectivity, right? We cannot design a perfect drug. We cannot design a drug that does not target off-target proteins, because proteins are there's so many proteins, and there's so many proteins that have very similar uh, structures, right? So we can't design an inhibitor by itself that can just bind to one oncoprotein that we want gone or inhibited, and then not bind anything else. That's what that's where these bad side effects from drugs come from. So now let's talk about why PROTACs maybe have a little bit of a better chance at being less harmful for people. So this isn't like set in stone because we haven't designed the perfect PROTAC yet. But because of this extra layer of selectivity that PROTACs have, they are less likely to form ternary complexes with off-target proteins, right? So that means that they're less likely to target off-target proteins and thus have negative side effects that we don't want. Now, there is a caveat to this in the sense that not yet. PROTACs are a new thing. Scientists have not yet designed a PROTAC which is capable of just like only targeting one. My point is just that if a drug were, if you were to take just abstractly just take inhibitors and PROTACs and say which one is more likely to be designed to only target one protein, it's always going to be PROTACs because they're more selective. So they have the potential to have a less dangerous impact on the on a person when taking it than inhibitors. It's just that we're not there yet because PROTACs are still a new thing. Now, because that toxicology segment was a little bit short, we're going to combine that with the resistance profile segment, which is one specific resistance that I found very interesting. Now, I'm not saying that this is more common or less common. Again, there's not enough data to support which one is more or less common between resistance to inhibitors and resistance to PROTACs. But what I can say is it's a little bit more specific in the sense that resistance. So we obviously know about the E3 ligase, right? This is the protein that is made by you. Your body makes this protein. Okay? So what happens is in people who develop resistances to PROTACs, what happens is their body stops synthesizing this protein. And I think that's a lot more specific than mutations to the protein. And I think that's a very I think that it could be more specific and thus a little bit less common, but obviously we don't know. Also, there's a number of other benefits to PROTACs. There's the lack of buildup of proteins. Because the target protein is degraded and not inhibited, there's a lack of buildup. So that also contributes to lower chance for resistances to be developed. And that's about it for this section. I just really wanted to highlight one resistance that I found very interesting. Next section is going to be the synthesis problems. What problems are scientists encountering, and what's the nature of that problem? Now to get into the synthesis problem. Spoiler alert, it's the linker. But let's talk about it. So let's talk about first what it means to synthesize a PROTAC. So conceptually, it's important that you understand this, but you have to you have a very, very small amount of anchors you can select from, and a very, very small amount of warheads you can select from. Why is that? Because you can only have certain molecules can bind to the E3 ligase you want, and only certain warheads can bind to the protein you want. Okay, so why does that make linkers a synthesis problem? Well, because if you pretty much can, these are pretty much functionally these are pre-selected. So your problem is, how do I make a linker molecule that can not only bring these two close together, but also provide that complementary surface interaction that we want so much, which is also dependent on linker length and orientation and a lot of other things. But this is the problem. There's a lot of research going into how can we design linkers. How can we? They're experimenting with different types of linkers. So obviously, the next video I'm going to make is going to be just comparing and contrasting a good amount of literature on linkers, right? But first, I do want to give us a little bit of background, which is what are the more commonly used linkers, okay? So we have PEG, which is usually just an ether, and then the more and more it extends, you just have another ether, and then stuff like that. Diether, triether, stuff like that. And then you have an alkyl linker, which is just a carbon chain. The reason these are so important, are so commonly used, is because length is extremely important for linkers, right? Because you have to have the proteins close enough to have these complementary surfaces, but you also have them far enough to where they aren't like super close, and then these interactions get scrambled, stuff like that. So these two linker molecule types are the most you can mess with the length a lot. Next video we're going to discuss like, hey, this is like cryosols, other types of linkers that aren't alkyl and PEG. But for right now, these understand that these two are very, very malleable in terms of length. But one of the issues we'll outline in the next video is that orientation matters. There's issues of, hey, can we actually ingest this drug with this linker molecule? Can it go through the cell with this linker molecule? There's so many issues with linkers. Okay, that's the think of this as like a little bit of a preview for next video, because the next segment is going to be a little bit about what is degradation. Why is degradation? Why are we being so careful with PROTACs? Now let's talk a little bit about the toxicology problem. And I would like to frame this problem as degradation versus inhibition. Why are toxicology profiles of... Now let's talk about the toxicology problem. I would like to frame this problem as an issue of degradation versus inhibition, kind of comparing toxicology profiles of PROTACs versus that of inhibitors. Okay? So I think the first thing I have to do is I have to explain why degradation is a lot worse than inhibition in terms of off-target proteins. So let's say you have a patient who takes an inhibitor to treat like a leukemia, right? And it works, and and then they have to get off treatment now that they have beaten this leukemia, right? What is very, very important is that shortly after they stop taking this inhibitor, the saturation of the drug goes down on the cells, and all of a sudden, all these off-target proteins affected by the inhibitor, they just stop. They're not affected anymore. The effects wear off because they're just being inhibited by the drug. As soon as the saturation decreases, they're back to normal. Degradation is a little bit different though. So first of all, you have to understand PROTACs aren't necessarily used up a lot of the time. So they are very, very potent. They can degrade a lot of proteins because they're just recycled. They're recycled into the E3 ligase, and then they just do it again and again and again until they degrade a lot and a lot of proteins of interest. Now, why is that important? First of all, you can't have proteins like that. You can't have drugs like that in your body and also target off-target protein because there's a chance they like maybe not like 70%, but they degrade a lot more of those proteins compared to off-target proteins compared to like inhibitor drugs. Second is degradation is a lot less reversible than inhibition. If you degrade a protein, your body now has to resynthesize that protein, which takes a lot more time than proteins that are inhibited that are off target. So the issue then comes when these scientists are synthesizing PROTACs is they have to be extra careful because they have to design they even on top of TK inhibitors being very selective when they're designed, they have to be even more careful because now the risk of off-target proteins is significantly more because even if there's one protein that's off target that's affected by a PROTAC, that protein is now going to be degraded constantly. So these are longer lasting effects of PROTACs, which is why the toxicology problem is so big for PROTACs because you have to figure out they have to make these drugs that are literally bind to one type of protein in the cell, which is so difficult. Which is why I think PROTACs they're definitely the next big type of drug. We have access to so many resources. We have access to so much technology. The chances that we develop a drug that targets one specific protein, on top of the fact that mechanistically it's a lot more selective than inhibitors, I think that skyrockets with PROTACs. But the problem is that it's maybe not now that a lot of them are approved for clinical usage because simply put, degradation is just so dangerous. You can't off-target degradation is a very dangerous thing. That's why a lot of PROTACs aren't approved for this wide use yet. And then there's also the issue of we'll talk about this in our later in the next video, which is perfect segue into the inquiry section of the video, which is the next video is going to be talking a little bit about linkers. It's going to be talking about what linkers are, what are the different types of linkers, and then they're going to be talking about different benefits of linkers, whether they're able to go through the cell membrane, the polarity that these linkers need to have, things like that. So thank you so much for watching this video. Have a nice day. Goodbye.